It's apparently complicated, but it's not. It's just a matter of being very careful. I hope that the premise is clear to you. Now, what we have to do is to compute the flux of energy. You remember the development of the CELC formula. So basically, we have to compute this. This one, EB. Okay. Let's go here. Here, I want to, given that XLC is evolving, the position of the shoreline is evolving at each time step, I want to create a copy in order to keep into memory the original position of the shoreline. Okay, let's do it. Plot was already done. Now we have to estimate the sediment flux. And the sediment flux is composed by 20 numbers. Actually, there will be not 20 because I have 20 coordinates, which means that I have 19 delta x. But so we will not be able to compute the flux of sediment in 20 locations. But let's define a variable, a vector, named QL, which has dimension 20, and therefore we will fill not all of them. So let's do this. Repetition 0, 20. I am defining this vector. Keep in mind one thing. When you define variables in R, you can basically you can avoid to define them. You can define them by assigning a value, like A equal 10. There are some languages that don't accept a solution like this. They first want that you say A is a variable, and then you assign the variable. When you say A is a variable, it means that you are defining the variable. R doesn't need it. And however, I think it is extremely useful that you keep defining variables. Why is that? Because for vectors, you need to define them. If I say A2 is equal to 10, what I get, let me see what I get. You see that what you get is not what you are expecting. So if you don't define a vector before using it, it's dangerous. And therefore, this is why I prefer to define QL before using it. And the way I define it is sorry, I remove A because I don't need it anymore. It's by giving zeros. So, if you say A equal repetition 0, 20, and then you write 8, 2 equal 10, if you display A, you are obtaining what you are expecting. So you are assigning only A2. What I did before without preliminary definition gave to me something that I did not expect. So be careful of that. I suggest that you define vectors in R before using them, even if it's not needed. And I think this is a weakness of R. R should require that you define variables and vectors before using them, like other programming languages, because it's clearer. It avoids mistakes. Given that when we program, it's extremely likely to make mistakes, of course, the programming language should be robust. In doing this, R is not very robust. So beware of this. Okay, so let's remove A because I don't need it. And now we vector QL that is defined. And this is volumetric sediment transport. It's expected to host the value of the volumetric sediment transport. And keep in mind, each time you have to recompute QL, because the shape of the shoreline changes. Even if the wave forcing doesn't change, the shape of the shoreline changes. Okay, now, look, we are at a critical point here, because we are starting the simulation. The simulation is to be repeated 1,000 times. So, a very nice feature of a program is that it allows you to repeat in a seamless way, so without any additional effort, the same instruction many times as you want. And this is very useful. It's like in Excel when you make a cut and paste. When you cut and paste, you repeat the same formula as many times as you want. And the same thing can be done here. And the way to repeat instructions in any programming language is through a cycle. These are called cycles. When you repeat the same instruction several times, it's a cycle. Each programming language has two key elements: cycles and conditions. The cycle is what we are now introducing here. Conditions, let's talk about them later. The cycle is to be repeated a fixed number of times. In our case, it's 1,000. The instruction that in R allows you to define a cycle is for. With this syntax, for, you need a cycle variable, which is in this case I, that is incremented by 1 each time the cycle is executed. It allows the PC to keep memory of how many times the cycle went on. And this I is varying in 1, double comma, and delta t, which is 1,000. Okay. And then what's follow? It's expected to be repeated 1,000 times. If what follows is more than an instruction, you need to put a curly bracket, which is expected to be closed later on. And everything is included in the curly brackets, it's repeated. Remember, this is the temporal cycle. This is cycle a long time. We will need to introduce another cycle in space, which is nested into the cycle a long time. Okay. Now, curly bracket, how to type it? Try to do this. Either you have an American keyboard, you have a key for the curly bracket, or you can try to do this. Let me see if it works here, because otherwise, let me see. Let me see if it works in a... Doesn't work. Ah no, I have, indeed, it doesn't work because in my keyboard I have the curly bracket. And it's let me see, it's this one. Okay. Okay. In my keyboard is Alt-GR, keep it pressed, Shift, and the E with the accent. If you don't have this key, you can try with Alt-GR, keep it pressed, and 8. Both of them, Alt-GR 8, or Alt-GR 7, I don't remember, let me check, because in my PC I don't have the curly brackets, so it's Alt-GR GR7. If you don't succeed, the last attempt is to search in Google, curly bracket. And then copy, let me see. I did this several times, like in this Wikipedia page for curly bracket, I select the curly, I copy it with the right or Ctrl+C, and then if you paste it here, you get the curly bracket. But I hope that you find it on the keyboard. Okay, let's go back. Curly bracket here. Okay. Now, it is not really worth pasting in R each instruction. It would be much better to copy the whole set of instructions in the cycle and copy them just once. Or source the original file in a way that I'll teach you later how to do. But in order to understand, let's try, in order to make it step by step, let's try to do, cut and paste one by one. Look what happens. If you create a fourth cycle and you press enter, R doesn't give you back the cursor, it gives you back a plus, which means I need some more. And if you put the curly bracket, it keeps printing a plus, I need more. Because it understands that there is a cycle that is open, so he waits for the final bracket. And if you type it, you get back to the cursor. And nothing was done, because between the brackets there were no instructions. So let's recreate it. Okay. And again, here we have another 4, because it's the spatial cycle. Okay. Okay, 2 4s, 2 cycles, no problem, it's a nested cycle. Okay, let's move forward. Now, let me draw on the blackboard what we are doing, and let me start from scratch. Okay, let's suppose that we are, and we indeed are, at t equal 1. At t equal 1, we have the initial morphology of the shoreline. And, okay, let's suppose that we have 20 points, but let's display only 3 of them. So we have one here, another one here, another one here. Okay, and here I have X, L, C1. Here I have Y1. And here I have X, L, C3 and Y3. Okay, there is an essential element that I need to estimate. this essential element is the angle between the wave and the shoreline. Do you remember? I go back to the CERC formula. I hope it's still here. At the end of the story, there is a sin alpha cos alpha. This is the angle between, which is also sin 2 alpha. It's the angle between the wave and the shoreline. So I have to compute it. So far, I know the angle between the wave and the y, which let me display in an intelligent way. The wave vector okay, let me put it like this. And the angle, but if I put it like this, the angle is close to 180. Let me do this. Okay, let's do like this. Okay, and I know this, which is alpha. Good. Now, I need another angle, which is the angle with the shoreline. And look, the angle, the direction of the shoreline is continuously changing. You have here one direction between the first 2 points and another direction between the other 2 points. It's better to estimate a local average direction. So it's better to, it's just a trick, or let's say it's just a way to ensure that the computation is smooth and the change is smooth. So because it's not really realistic that the direction of the shoreline suddenly changes between one point and the other one. Actually, we have a gradual change. So it's better to estimate an average direction. And the average direction is obtained by computing a local average, and therefore connecting these 2 points. So what I'm interested to compute is this angle here.
Also, if I have 10 points, I connect it first with the last one.
No, let's assume that we connect only the closest 2. So, for computing the sediment transport in the first step, I take an average direction between the initial point and the following one. When I go to this step, I keep the average with the next one. Okay, I take only 3. But this is a matter of your personal preference. You may decide also to apply, to look only at the local angle. It's just suggested, I found out that this is what the literature suggests when your step is like, in this case, 150 meters. So if this step is very long, it means that you may have indeed sharp changes in the shape of the coastline, because the spatial step is coarse, it's not fine. If you have instead a survey that gives to you a very fine representation, you may also look only at the local slope. It depends. In this case, let's assume that we take an average by, when we refer to this first delta S, we take an average between the first and the second. Okay? Okay, so I am interested in this angle. It can be computed for sure if we find a way. It can be computed for sure because I know the coordinate of these points, and therefore I can compute the slope of this segment, and therefore if I know this angle, I can also compute this. We have to find a way to compute it in a clear way. Okay, so let's first of all compute what? this one. Do we agree? It's the same. Okay. So if we could find a way to compute this angle here, which I call alpha 1, by subtracting alpha minus alpha 1, I could find the angle I am interested in. Okay? Alpha 1 is also this one. By the way, you have this video in the PDF. Just 1 second, I get it back. If you go to the second page, this is the same video. Sorry? Okay.
But why is also the alpha 1 on the top?
No, let me see. Did I make? Okay, no, it's this one is. Let me see. No, it's this one. Sorry. It's this one. Is it correct? Yeah. This one. Okay. And I think here is correct. Yeah, here it's correct. Okay, now let's put in evidence, let's highlight that this is 2dy and this one is x and c. I plus 1 minus x L C I minus 1. So I know the elements of this rectangle triangle. I hope in English it's correct.
Right.
Sorry?
I think right triangle.
Say again?
Right triangle.
Right triangle. Okay, thank you. Thank you. Right triangle. And how they are called the segments in Italian, we say cateti. Do you know?
The segments.
The segments, basically. Yeah. This is the right triangle, correct? These two segments.
But this one has the 30 and
Sides.
It
Okay,
has
the
the
sides.
30 degrees and 60 degrees. This one is like right isosceles, or just right.
No, it's just right.
Right.
Sides, okay? Thank you. Because and also
And also, this angle is called obtuse.
obtuse, okay. Obtuse, I know what it means. And can I say acute also?
I haven't heard such.
What is the
Obtuse is
Obtuse,
the right angle. That is, it's mathematics.
no, obtuse means more than 90.
Yeah. No, it's more than
Obtuse,
obtuse.
Obtuse angle more than 90 degrees.
yeah, obtuse.
Should be the lesser one.
And less than 90 is acute. Okay, but acute. Okay, perfect. And so you can help me. This is interactivity. And how do you call in Italian? I would say lati, meaning if I have like a square, each of the segment has a name. It's called we call it lato. Side. Okay, side. So the sides is what you said, the sides of the right triangle, it's like cateti, yeah, because, okay. Do you know the word cateti? I think it's from Latin. No, okay. I think it is from Latin. Anyway, sides. Very good. Okay, so we have each side of this right triangle, so we can compute the angle alpha 1. So, basically, let's compute alpha 1 then. We can say that 2dy is equal to XLC. Okay, let me call this delta x. 2 delta x, which is not correct really, because I should write it this way, because it's not constant, it's not, let me correct delta x, because otherwise it's misleading. Okay, so 2 dy is equal to delta x times, I think it's cotan, let me see. One side is equal to the other side for the cotan alpha 1. I think it is correct in this way. Which means 2 dy is equal to delta x divided by tan alpha 1. If I'm not mistaken, this is, and therefore I can write that tan alpha 1 is equal to delta x divided by 2 dy, and therefore alpha 1 is equal to a tan delta x divided by 2 dy. I think this should be correct. If it's not correct, okay, we'll check. We will check if it is correct or not. Okay, let's see if it is correct. Let me look at the website. You see that there is a variable that is defined, which is XLC aux, which is the difference, it's my delta x. XLC aux is my delta x. So let's compute it. Let me see if I already opened the cycle. Okay. And this is my, again, my delta x.
Why did you use double I in the cycle? Because is it the second loop?
It's a second loop.
It starts from 2.
No. It's the second loop. You need a different index for the cycle. It could be AA, whatever. But must be different with respect to I. Okay? II doesn't mean that it's 2 i's. It's just a different name. Okay? Okay, let me just copy now alpha 1, and indeed what I wrote there is correct, according to, it's the same that is written here. Now I need to compute an average wave height. So, keep in mind that we are starting II, this is important to note, starts from 2. Why from 2? Because given that in order to compute the average coastline, I need to refer to the previous point, I cannot start from here. I need to start from here. Okay. Now let's compute the average wave height. HB aux. This is computed in a weird way. I want to change it because it makes an average only between this point and the subsequent one. Let's take an average of wave height over 3 in analogy with what we did before. Okay? These are all numerical approximations, so you can decide whatever you think is reasonable. I'm taking these averages in order to smooth the computation. Okay? But in this case I want to change it. I want to change. Let's HB II minus 1 plus HB II plus 1 plus HB II divided by 3. Good. So I made a change with respect to the file. I will change it. And I will change it with substitute on my website, but give me some time. I may take a couple of days to change it. And this is, again, what is this? Is wave height, averaged over 3 points. Be careful, this is slope of the beach and beach grain diameter. Look at what's written here. It's not used unless one uses other formulas than CERC. I took this program from the web and I modified it. I modified it because I wanted to adapt it to R. It was not for R when I found it. And the program was conceived for applying, besides the CRC, other formulas, and therefore it needed the specification of the beach slope and grain diameter. I decided to leave them there because I think it is useful that you see that indeed this information could be used by other relationships. Okay, let me do like oops. Sorry. It is really not efficient to put this information into a cycle. This is an information that should be placed above, out of the cycle, because it's meaningless to repeat the same information that doesn't change so many times. But anyway, let's leave it there. And now, these are just test instructions, but don't forget about it for now. Now let's compute the energy and energy flux. The theory is here. Energy flux, and here you need, in order to compute the energy flux, the wave group velocity, and you need the depth of the sea bottom besides the wave height. What you see here in this web page is translated here into these instructions. Good. Now I am ready to compute through the CERC formula the volumetric sediment transport rate. I'm not sure whether I computed. Let me see. I'm using this angle here. Okay. Okay, I'm using alpha 1 and not alpha 2. I told you before that I wanted this angle, indeed, which is the same thing. I'm using alpha 1, more or less the same thing, let's say. But in this case, let me think about it. I'm not sure whether this is correct. Because, okay, let's cut and paste and then close the full cycle, and then there is another question. No, sorry. Okay, I can repeat them, no problem. Let me see. Yeah. And okay. Let's forget about the open question for now, okay? Okay, yeah. And now I can close the cycle. The first one, the spatial cycle. So by closing this spatial cycle, what did I compute? I completed the computation of a long-short sediment transport at each spatial step for the first time interval. And now I'm ready to compute the difference between these long-short sediment transports in the various spatial steps in order to determine whether there is accretion or erosion. So let's compute the difference. And diff, this instruction computes the difference of the vector QL. Be careful, the resulting vector is counting one less element with respect to QL, which is normal. If you have a vector of 10 elements, 20 in this case, not really 20 because they are 18, because my cycle goes from 2 to 19. And if you have a vector with 18 elements, the differences, the vector of the differences is 17 elements. Okay? So, let's go here. This is the difference. And now we are ready to compute for each spatial step. So we need another spatial cycle, the Xi. So we need another spatial cycle. There is a negative sign here. Let's open another question. We have two open questions. Okay? First, I had a doubt on the value of alpha 1. If it is correct here to put in a computation of QL